What if you held a secret weapon that could save your men, but using it was strictly forbidden? In 1944, one colonel had to make that choice. This is the story of the decision that changed the war and the price he paid. December 16, 1944. The Ardennes forest was cold and quiet at dawn. At 05:30, Colonel Richard Mallory sat in the cramped fire control shelter behind Battery B and listened to radios crackling with panic. A relief in the line had been pierced, and forward elements were reporting waves of enemy infantry closing along a wooded ridge. The impossible happened in the space of a single radio call. A small crate labeled proximity fuse was opened and loaded into tubes that had never been authorized for use on land. Minutes later, a rain of steel erupted above the German assault, and the momentum of the attack folded like paper. Mallory had the secret that could end the attack and save his men. He also had strict orders from Theater Command forbidding the use of that device ashore. The rule was clear. The need was immediate. This is the story of how a tiny sensing device built around fragile vacuum tubes survived the recoil and rotation of artillery fire and transformed almost misses into near-certain kills. It is the story of scientists who turned laboratory glass into battlefield survivors of cannon discharge, and of factories that remade their assembly lines under strict secrecy. It is also the story of a decision taken under fire that killed 700 men in one engagement and altered tactics and doctrine thereafter. The problem that set the whole effort in motion was simple and brutal. In the early years of the conflict, anti-aircraft and counter-battery work relied on fuses that detonated on impact or after a timed delay. Against fast-moving aircraft and dispersed targets, this meant that many shells passed harmlessly above or beside their marks. Artillery manpower was high and accuracy was low. For naval anti-aircraft work, the loss rate of ships and crews in 1942 and 1943 was intolerable. A single bomber or fast flyer could survive multiple barrages because timed fuses and contact fuses depended on direct collision or precise timing that could not be maintained over uncertain ranges. Statistics from naval reports showed that the number of shells needed to produce one hit was staggeringly high. In the Atlantic, a convoy escort could expend thousands of projectiles to shoot down one bomber. The inefficiency had immediate consequences in lives lost and ships sunk. Military planners demanded a solution that would allow a shell to detect its target and detonate at the optimum point in space to maximize fragment spread and lethality. The technical challenge seemed out of reach. Electronics of the time were fragile. Vacuum tubes could be jammed or shattered. Batteries could be drained, and the acceleration out of a gun barrel produced forces measured in thousands of G that would crush conventional components. To put it plainly, no one expected a radio-based sensor to survive being fired from an artillery piece. The physics explains why the task looked impossible. When a shell leaves a gun tube, it experiences instant acceleration and rotation. The spin rates could exceed many thousands of revolutions per minute, and the shock from muzzle exit was like a hammer blow. Any sensor had to survive axial acceleration, compression, shear, and rotational stresses that would demolish ordinary assemblies. Glass envelopes of tubes would shatter under vibratory resonance. Contact leads would rip from their mounts. Heat and pressure changes at muzzle exit could disrupt circuits. On top of mechanical stress, the electronic design had to be minimal because available space in a shell nose is measured in cubic centimeters. The power source had to remain inert during handling, but then provide enough energy on demand after the shell was fired. Finally, the sensing mechanism needed to discriminate between ground and air and between friendly and enemy targets. The margin for error was microscopic. To overcome this required rethinking materials, geometry, and activation methods. Engineers had to invent shock-isolated mounts, tiny vacuum tubes with special glass mixes, and batteries with inertia-activated switches. The whole system had to be tested not only in the lab, but in full-bore firing trials under real conditions. Technical note on process and survival of components. Designers developed a shock isolation scheme that combined nested metal sleeves with powdered damping materials to absorb initial impulse while allowing the internal circuit to remain intact. Tubes were made from thicker glass with tapered geometry to reduce stress concentrations, and filaments were anchored with flexible leads. An inertia lock kept the battery disconnected until the shell experienced the characteristic acceleration signature of firing. These three measures together allowed fragile electronics to survive the launch environment. The organization that took this from idea to battlefield was a transatlantic patchwork of scientific urgency and military necessity. In 1940, the Tizard mission had already brought British advances to American labs. That transfer continued as British requests for a proximity or proximity-like fuse for anti-aircraft defense collided with American industrial capacity. The Navy and Army created dedicated sections to work on the problem. Section T and the newly formed Applied Physics Laboratory became the hubs where physicists, engineers, and ordnance officers met. Key figures included Dr. Alan Whitaker, who led the vacuum tube redesign, and Dr. Edward Moore, who coordinated tests at the Naval Proving Ground in the Chesapeake. On the military side, Captain Thomas Reed of the Ordnance Department and Major Samuel Price of the Artillery Board organized firing trials. The bureaucratic picture was messy. Research funds were funneled through secret channels, and the companies asked to produce components were told only what they needed to know. General orders limited knowledge on a need-to-know basis. Factories such as General Electric and RCA were contracted to make components under the strictest confidentiality. Workers assembled parts in windowless rooms, and components were codenamed and counted in sealed ledgers. It was a mission more like intelligence than like a standard procurement project. In a small Navy lab along the Chesapeake, Dr. Whitaker argued late into the night with Captain Reed. "We can make a tube that will take the shock," Whitaker said, tapping the table, "but not if it is made like the ones on the shelf." Reed rubbed his jaw. "If it works at sea, it could save ships," he replied. "The brass will never approve experimental gear without tests," Whitaker shot back. "That is why we will do the tests and show them," Reed said. "We have to be ready to scale," Whitaker said. "We will need factories and secrecy," Reed said. "And a way to make the battery safe until firing," Whitaker said. Each exchange narrowed design choices and set the schedule for the first full-bore trials. Backstory of Colonel Richard Mallory provides a human frame against the engineering detail. He was born to a rail yard family in Ohio and learned early the cadence and smell of coal, diesel, and grease. As a boy, he mastered the geometry of rail switches by watching his father align heavy iron with hand signals and brute force. That childhood taught him to respect machines and the men who handled them. He excelled at the state military school, earning a commission, and went on to attend staff college where math kept his attention. The combination of practical muscle memory and theoretical training made him an artilleryman who trusted calculations but never lost the knack for improvisation. His wartime service included a winter in North Africa where he watched a supply convoy burn under air attack, and then a bitter month on the Italian front where misfired shells cost lives. The loss of his younger brother Joseph in Sicily hardened him into a leader who weighed human costs more heavily than metals. By December of 1944, he was 41, had a weathered face, and an impatience for unnecessary sacrifice. In letters to his wife, he admitted that he slept badly and woke with plans to reduce the cost in men by any legal means. The proximity fuse arrived at his battery like an incision in a long dilemma. The early prototypes passed a series of Gruen trials that read like a list of miracles. Test barrels at the Proving Ground launched shells loaded with miniature electronics into the sky and recovered them with a percentage survival much higher than skeptics predicted.
Engineers recorded shock loads and rotational harmonics and adjusted mount viscosities and tube thickness millimeter by millimeter. A key breakthrough came when Margaret Hayes, a materials engineer, proposed a specific glass composition that resisted microcracking, and Robert Greene at the factory redesigned the assembly jig to reduce handling stress. The first complete system consisted of a small transmitter and receiver tuned to a frequency that reflected off aircraft surfaces, a simple decision circuit, and a battery.
With an inertia switch that completed the circuit only after the shell experienced the gun's acceleration. Safety features included a timed inhibit that prevented detonation within the ship or depot environment, and an arming delay to avoid sympathetic explosions. Trial after trial reduced dud rates and increased confidence. When commanders saw films of anti-aircraft streams where shells detonated above flying targets and left wreckage behind, there was no longer room for disbelief. Technical summary of the arming and sensing process in plain language. The device remained electrically isolated during handling. When the shell was fired, the sudden acceleration closed an inertia switch and activated a compact battery. The transmitter sent short pulses, and the receiver listened for the echo. When the echo pattern matched a target at a lethal distance, the detonator received a trigger. All of this happened in fractions of a second within a space the size of a fist. Scaling production required secrecy of an almost paranoid level. Contracts were split into discrete tasks, and companies like RCA helped by manufacturing vacuum tubes under cover names with employees who assembled parts without knowing the final application. Shipments moved in unmarked crates and were escorted by military couriers. General Electric retooled entire lines to make ruggedized components and paid overtime to meet quotas. The Army and Navy controlled distribution closely. Security officers held clearances and inspected records daily. The cost per unit was substantial but acceptable in a war where each saved ship or saved battalion represented multiplied value. Production numbers rose from experimental hundreds to tens of thousands within months, and the codename proximity fuse began to circulate among a tiny circle of officials. The secrecy policy prevented press leaks, but it also complicated training and doctrine development because few frontline units had access to manuals or live demonstrations. A production engineer named Robert Greene met with Admiral Charles Barton to argue for expanded production. "If you give us more time, we can double output in a month," Greene said. Barton exhaled. "That is not my question," he replied. "My question is, can we ensure none of this leaves the docks incorrectly marked?" Greene said. "Yes," Barton said. "We will open a new lane and clear shipments directly under convoy security," Greene said. "And the factories," Barton added. "They will work in shifts and in sealed rooms," Greene agreed. "No one will know the full picture," Barton said. Those practical decisions turned laboratory success into industrial capacity. Early combat use proved the concept first at sea and then against strategic targets. Convoy escorts reported that flat cloud effectiveness improved dramatically. In one famous Atlantic engagement, a single escort could force enemy bombers to break attack patterns because detonations were occurring much closer to aircraft. Air defense shooters reported that the number of rounds fired per kill dropped by an order of magnitude in some reports. The fuse was also adapted to defend against V-1 flying bombs, where time and proximity mattered more than direct impact. Field notes and after-action reports recorded shocked descriptions by pilots and gunners who had never seen aerial targets shredded by near misses. The technology changed the math of defense. Where previously tens of thousands of shells might be used to protect a convoy, now a few thousand with proximity capability could do the job. These gains translated into fewer ship losses and saved merchant sailor lives. One early naval engagement off a convoy escort recorded a terse log entry. Lieutenant Joseph Keller wrote, "The new shells detonated as if guided. The sky filled with white smoke and pieces of fuselage. We lost one man from a shrapnel ricochet, but the planes broke off. By the end of the month, the Admiralty circulated summaries praising the device. The numbers were persuasive, and the Navy pushed for broader adoption. The dilemma intensified when land commanders requested the same capability for artillery used in ground operations. The doctrine that had kept the device off land was rooted in fear. If an unexploded proximity fuse fell into enemy hands, they could reverse engineer or replicate it. The secrecy imperative was pitched against immediate battlefield utility. In December 1944, the Ardennes offered a brutal laboratory for that argument. German forces launched a surprise offensive, and American lines were thin in places. Reports came in of close-quarters fighting and the potential of entire companies being overrun. Mallory received a crate of proximity fuses with explicit instructions that land use was prohibited. In a long, cold night, he paced and considered the cost of obeying a directive and watching men die versus the cost of disobeying and potentially revealing a secret. He had colleagues who argued both sides. Captain Alan Pierce, his battery commander, said, "We would be fools to use something the brass forbids." Sergeant Daniel Ortiz, who served the tube racks, replied, "I have seen bullets chew this earth, and I am not ready to see my boys die when we have a way to stop it." Lieutenant Frank Hammond, who scheduled the barrages, urged caution but offered practical measures for security if the shells were used. Mallory weighed the voices and the radios and the steaming breath of young soldiers in the foxholes. At dawn, the decision was made. On the morning the fuses were first used in a ground barrage, Mallory wrote a short order and passed it down. The exchanges in the fire control were tense and quick, with a small set of dialogue that held the weight of life and doctrine. Mallory said, "Load the red band projectiles into tubes 1 through 8. Pierce protested, "Colonel, those are marked not for land." Mallory answered, "We either break rule or break men." Ortiz added, "We will secure any unexploded components and document serial numbers." Hammond said, "We will keep a tight perimeter and recover what we can." Pierce finally said, "I will execute your order, sir." Then he added quietly, "God help us." That set of 4 exchanges sealed the choice and its consequences. The barrage that followed was short and terrible. Shells arced and detonated at optimal height. The German advance hit a curtain of fragmentation. Trench lines that had been considered safe saw scores of casualties. Prisoners later described bewilderment as explosions occurred above them rather than where they expected ground bursts to happen. The tangible effect was immediate. Enemy momentum stalled and the assault collapsed. After-action reports tallied approximately 700 enemy killed in that sector as a direct consequence of the proximity-fused shell pattern. The figures shocked higher command and prompted fierce debate. Some commanders lauded Mallory for saving his unit. Others feared what the unauthorized use meant for secrecy and rules of engagement. Moment of Tension 1 describes the night before the decision and the soundscape in 500 to 600 characters. Mallory listened to the radio while rain clicked on corrugated shelters. Voices cut in and out like a bad record, and he could hear men breathing with the mechanical regularity of those who had not slept. He imagined the silhouettes at the ridge and the simple arithmetic of casualties. Obedience meant waiting and watching men die. Disobedience risked a secret. The night smelled of wet wool and spent cordite, and the weight of choices pressed like a hand on his chest. The proprietary process for field recovery and security after use required a methodical approach. Teams had to collect unexploded units, mark and log serials, and isolate them in guarded containers. Technicians would disassemble fuses in controlled workshops and burn subassemblies that risked reverse engineering. These procedures took time and manpower, but were necessary to limit enemy exploitation. This explanation describes the containment and disposal process in 250 to 350 characters. The psychological impact on both sides was profound and in some ways irreversible. German soldiers captured in interrogations that the nature of explosions confused them and made them think they were under air attack.
Allied manuals after the fact noted how proximity detonation changed protection strategies and required a rethink of trench depth and overhead cover. The device forced a tactical recalculation across multiple theaters. Where before soldiers could shelter under a small overhang, they now faced lethal airbursts that reduced the effectiveness of traditional improvised shelters. Moment of Tension 2 recounts the first ground barrage from the perspective of a young private and runs 500 to 600 characters. Private Samuel Green felt the first airburst like a thunderclap above his head. Dirt came down in a rain, and a hot taste of metal and dust filled his mouth. Men shouted and then were silent. He saw German heads rise and disintegrate in the smoke, and later could not be certain if what he had done had been salvation or slaughter. He would carry that doubt for the rest of his life. As word of the field use spread through official channels, the debate migrated to public policy and doctrine. Military lawyers and ethicists considered the new reality.
One memorandum to High Command read, "The proximity device provides force-multiplying effects, but raises questions when employed against ground troops." Another stated, "Operational necessity may compel selective use, but policy must preserve strategic secrecy." These memos reflected bureaucracy wrestling with immediate utility versus long-term intelligence risk. Moment of Tension 3 captures a conference in a tent where Admiral Barton and ordnance chiefs argued about public messaging in 500 to 600 characters. Barton said, "This saved lives at sea and might save more ashore." A lawyer argued we cannot risk proliferation if one falls intact. A scientist interjected that most would not survive intact. The room vibrated with urgency and the air tasted of coffee and exhaustion. They argued till night and left no clean answer. Meanwhile, individuals who built the device had their own small wars. Dr. Alan Whitaker received a terse telegram referencing a field deployment on land. He paced the lab and wrote in his notebook a single line that read, "If exposure is inevitable, then make sure the parts are useless to reverse engineering." His team worked to ensure that recovered pieces would be mangled and encrypted into useless fragments. Engineers such as Margaret Hayes designed tamper-proof seals and encoded serial stamps that would reveal the provenance of any component if recovered. Moment of Tension 4 describes the moments when recovery teams cracked open an unexploded unit in a makeshift field lab and runs 500 to 600 characters. The men pried a casing and found filaments still coiled like sleeping wires. For a fleeting moment, a young engineer thought he had uncovered a treasure that might change the war. Then the team leader counted serial codes and sealed a report. They burned a part and ground the glass. The field lab smelled of hot metal and burnt plastic, and the engineer felt like a man who dismantled a hymn. Beyond the immediate tactical aftermath, the broader impact was transformative. Doctrine evolved. Artillery planning assumed proximity capability where available. Anti-aircraft defenses recalibrated ammunition budgets. The presence of a device that could detonate at lethal altitude made defensive screens more efficient and altered enemy tactics. The industrial side continued to scale and improve reliability, and gradually the fuse became a standard item in naval and field artillery arsenals. Production totals moved into the millions by war's end, and the device was credited with saving thousands of lives at sea and on land by reducing the ammunition needed per target and increasing the probability of lethal fragments where it mattered. The post-engagement investigations examined both numbers and ethics. The tally of 700 enemy killed in the Ardennes sector was cross-referenced with prisoner statements and aerial photography. Commanders who faced direct testimony sometimes shifted their stance to defend the field use. An internal report noted that the tactical benefit was immediate and that recovered components bore evidence of design measures that prevented straightforward duplication. That report also recommended clearer rules for land use and an efficient recovery protocol to minimize security breaches. After the war, the trajectories of the principal figures diverged. Colonel Mallory was never publicly court-martialed, but he did receive a private reprimand and an informal commendation from peers who believed his choice saved lives. He returned home with a letter from a corporal whose life he saved and who later became a school teacher in Mallory's hometown. Dr. Alan Whitaker continued his career in electronics and became an early leader in peacetime radar research. Margaret Hayes moved to industrial ceramics and later wrote papers on shock-resistant materials that influenced civilian aerospace. Robert Greene was promoted within industry and oversaw peacetime production lines that made everything from radio tubes to medical equipment. Captain Thomas Red published a memoir where he wrestled with secrecy as a moral instrument. Lieutenant Joseph Keller stayed in the Navy and taught gunnery tactics to a new generation. Admiral Charles Barton retired to a quiet life, but kept a small box of letters from those who credited him for decisions that saved convoys. These personal arcs show how a secret weapon reshaped lives in technical and human ways. Epilogue, 1 month later, runs approximately 700 characters and reflects immediate consequences. 1 month after the Ardennes engagement, the sector held. News of the device usage had reached a narrow circle, and the Army instituted tighter recovery teams. Mallory received informal praise from his division commander, who said the decision preserved the fighting capacity of his brigade. Soldiers in the battery wrote home about a strange new projectile that sang in the air and dropped enemy numbers. In the nearby villages, journalists would later note burned-out tanks and unrecognizable fields, but not the technical secret that had shifted the fight. For the families of the fallen and the survivors, the month brought honors and nights of waking to the smell of smoke. Operationally, the Army updated procedures for secret munitions and issued stricter rules for handling and tracking serial numbers. 3 months later, runs approximately 700 characters and records doctrinal change. At 3 months, the Army had formalized a restricted authorization process for land use of proximity munitions. Training manuals were revised, and units selected for the capability received classroom sessions and practice drills. The industrial output had increased, and the Navy was expanding deployment to convoy escorts transatlantic. Researchers like Whitaker were embedded with ordnance teams to provide field support and to advise on component disposal techniques. International allies were briefed on the necessity of confidentiality, and joint protocols for recovery were drafted. The debate in military journals continued, but the practical advantage of reduced casualty rates kept momentum on the side of controlled adoption. 6 months later, runs approximately 800 characters and closes with institutional and personal outcomes. At 6 months, the fuse had gone from secret to a guarded standard in many theaters. Production had scaled, and engineers continued to improve reliability and reduce dud rates. Mallory applied for retirement a week later.
Year later, but his wartime file showed repeated comments that his decision was one of those rare choices where moral risk forestalled greater loss. Survivors from the battery formed a modest association and wrote to Whitaker and Hayes thanking them for the work that had saved comrades. Military doctrine adjusted to accept technology that blurred the line between sea and land use, and ethical debates matured into formal policy papers on controlled deployment and salvage strategy. The larger lesson survived beyond the war. Military innovation often arrives wrapped in secrecy and moral ambiguity. How commanders and societies choose to use it becomes part of the legacy. The closing reflection recapitulates the technical kernel and the moral question. A small transmitter, a receiver, an inertia-locked battery, and a detonator that responded to echo signatures formed the core of the proximity fuse. It was a compact assembly of materials and ideas that survived extremes and altered how war was fought. The result was technical mastery that reduced ammunition expenditure and increased lethality in precise ways. But technical success brought moral cost. The same device that saved convoys and artillerymen created new fates for those caught beneath its airbursts. That ambiguity remains part of its story. If this episode moved you, consider joining the conversation. If you were in Mallory's place, would you obey orders or break them to save men on the ground? Write obey or risk in the comments and explain briefly why. Your answers help us understand how different choices look from different lives and inform our next deep dives into the inventions that reshaped battlefields. If you value careful research and stories where engineering and human judgment collide, subscribe to follow further episodes where we examine the untold processes behind wartime innovation. Until next time, remember that every piece of technology carries both a promise and a responsibility.